Hello, I'm Omid from KU Leuven and here to present our paper on the impact of applying machine learning in the decision-making of self-adaptive systems. Here is the architecture of a self-adaptive system with a machine learner and a verifier. The managing system solves an adaptation problem. In concern of decision-making in self-adaptive systems, the adaptation problem is selecting the best adaptation option. Subtask of the adaptation problem is delegated to the machine learner. For example, keeping runtime models up to date or reducing large adaptation space. And subtask of the problem is delegated to the verifier to analyze adaptation space to guarantee the adaptation goals. In this paper, we focus on an instance of the general case that we have explained in the previous slide. For the adaptation problem, the focus is on ensuring an optimization goal for a system, for example, ensuring that the packet loss of an IoT system is minimized. The learning problem is making predictions for a system property using a regressor to support analysis, for example, predicting the packet loss of all the adaptation options to reduce the adaptation space based on a threshold. The verification problem is making estimates with some degree of accuracy and confidence to support the decision making using a statistical model checker. We found that machine learning methods offer a variety of use cases for supporting self-adaptation. However, since machine learning methods apply in a sense statistical methods, they may have an impact on the decision made by a self-adaptive system. So the research question that bubbles up here is, what is the impact of applying a machine learning method on the analysis results under the specified problem focus? To answer this question, let's look at the model of the supervised learning from a statistical perspective. The first component in this model is a random generator of independent, identically distributed, in short IID vectors from a fixed and unknown probability distribution function. The other component is a supervisor that returns an output y for every input x based on a fixed and unknown conditional probability distribution function. And finally, there is a learning machine that selects a function from a set of functions such that it obtains the best approximation for the responses of the supervisor. But how this function selection is done? It's based on first a loss function that defines a distance measure on the predicted target value and the real target value y, and second based on a set of IID training data. Eventually, the learning machine attempts to minimize the empirical risk, which is the loss function's average on the training data. Okay, now let's see what's happening when applying the machine learning to reduce the size of adaptation space for the verification. Based on the pre-training data, the regressor predicts the quality attribute Q for all adaptation options. Then based on the prediction results, all configurations whose quality value is predicted to be less than to a cutoff value are included in the reduced adaptation space. Now suppose that the value of best option from the verification of the reduced set is denoted by b hat. On the other hand, suppose that the value of the true value of the best option among all adaptation space is denoted by b. Now, to measure the quality of the reduction method, we need to know the distance of the selected best option with the real one, or mathematically knowing that what the difference of b and b hat is. For the properties of the SMC, we know that if the estimation error of the statistical model checker for the quality attribute Q is denoted by kappa and no reductions happened, the probability that the specified difference would be less than the estimation error is greater than the confidence level of the SMC. And now the realization of the research question on the impact of applying machine learning and the analysis result is how this formula will be changed by utilizing the regressor to reduce the adaptation space for verification. This theorem is an answer to this research question and the main result of this paper. As you can see, different factors are involved in this new probabilistic bound. One of them is the number of training data that has been collected for training the regressor. By increasing this number during the time, the value of delta and consequently the value of h will decrease. So we obtain a tighter bound for the difference. In other words, it means by knowing more training data, we can estimate the difference more accurately. That makes sense. Another variable is eta, which is a free variable and set by the designer. Although increasing this parameter can decrease h, it decreases the probability of the bound as well. So, and another affecting factor is the parameter d that indicates a concept in computational learning theory called VC dimension. Actually, it's a measure of the capacity of the learner. It is determined based on a set of loss functions that the learner defines. Finally, this term is the probability bound, estimates the probability that at least one of the options in each neighborhood of the best option located in the reduced set. We evaluated the introduced probabilistic bound through Delta IoT, an IoT network with 37 modes and 1 gateway. The adaptation goal is to minimize the packet loss in the network for a given power setting of the modes to communicate data. Managing system in this application exploits a regressor that predicts the packet loss of 4096 possible network configurations. The predictions are used to reduce the adaptation space based on a cutoff value C. And to predict the value of the packet loss, we use the following verification query on polysom C. As a result of the evaluation in this figure, you can see the cumulative number of training data that are used by the regressor to update its learning model over 200 cycles. We distinguish two phases marked by the red dotted line. During the first 30 cycles, the learning model is trained but not used for adaptation and space reduction. From cycle 31 onward, the learning model is used to reduce the adaptation space. The gray dotted line here in this figure shows the theoretical bound of the packet loss error with adaptation and space reduction. It shows that the absolute difference between the value of the best option in the reduced and complete set is less than the specified bound with at least a probability of 0.5. In this experiment, alpha and epsilon are corresponding parameters to the statistical model checking and the verification query. As we are using the packet loss percentage, we need to multiply the query result into 100. So the final estimation error of the query is 100 times of the epsilon, and the range of the attribute is from 0 to 100. For the VC dimension of the learning method, as we are using a linear regressor on input data with 85 dimensions, we can say it is 86 based on a lemma in computational learning theory. In sum, this paper contributes a theorem that defines a theoretical bound for one instance on the impact of applying a machine learning method. The work presented in this paper can be extended to classification tasks that apply for the decision making of threshold goals. Also for other types of learners and other use cases of ML methods, other analysis methods may need to be investigated, for instance, for reinforcement learning methods. Finally, we also need to think more about using other concepts such as the Rademacher complexity as an alternative way to obtain a tighter version of this probabilistic bound. Many thanks for your attention.